electric dipole. So I've made this video before. I'm going to make it again. This with better graphics and better equations and everything like that. So let's look at the electric dipole. So this is, I'm not going to go over this animation, but I will do live coding at the end, but not this. But if you want this, let me know, because you know I'm here just to do whatever you want. So here, a dipole is a positive and a negative charge separated by some distance, and this is the electric field around there. Let's look at finding the value, the magnitude of this field. So imagine, let's just review, just a quick review. So imagine I have some point charge right here, Q1, and there's my origin. And then I want to find the electric field at some other location. I'm going to call this OBS, for observation location. Well, how would I do that? Well, the first thing, I need to know the vector location of charge Q1. I'm going to call that R1. And then I need to find the vector location of the observation location. I'm going to call that RO. The O stands for observation. And from that, I can get the vector from the charge to the observation location. So a lot of times we just think about the charge at the origin, and that's easy, but we can't always do that. So this is just the generic version. And then I can calculate this vector R, right? It's just going to be this position vector RO minus the initial position. It looks just like a displacement vector, right? Delta R. It's the same thing. Now I want to calculate the electric field. We can do that with the following equation. The electric field at this point is this constant 1 over 4 pi epsilon naught times the value of the charge Q1 divided by the magnitude of this distance. It's a vector, so I got to take the magnitude and then square it. And then I have to multiply by r hat. That's very important, right? Because this is a vector, E is a vector. That's a constant scalar once I take the magnitude. So if I don't have r hat, I don't get a vector. And if you don't have a vector, you can't do real calculations with the electric field. So r hat is a unit vector in the direction of r, and we can calculate that as the vector r divided by the magnitude of r. Okay, so that's how we find unit vectors for anything. And if you do that for a point charge, this is just for fun. This is what the electric field due to a point charge looks like. It points outward away from that charge because that's the direction of r, and it gets smaller as you get further away. So again, I'm not going to show you how to make this. I've made this in Python. We're not going to do visualizations. We're just going to do calculations, but I will do live coding at the end. So what if you have more than one charge? What if I have two charges? Q1, Q2. Well, if I want to find the electric field at some observation location, then I need to find the electric field due to charge 1, the electric field due to charge 2, and then you can add them together as vectors. That's the key right there, right? That's why it was important to have E1 and the E2 as vectors. Otherwise, I can't add them as vectors. So you got to do that. And then the total electric field is just the vector sum of those. Okay. Dipole time. So a dipole is two charges, a positive and a negative, equal and opposite charges of value Q, and they're separated by a distance S. Okay, so I put this on the x-axis with the center at the origin, and I have a negative Q on the left, and we all know that negative charges are blue and positive are red. You know that, right? I'm just kidding. I always do it that way, though. And then they're separated by a distance S. So imagine that I want to find the electric field due to this dipole at some location down here. Well, I mean, it just doesn't matter that they're positive and negative and separated by a distance. It doesn't matter, right? I still say calculate the electric field due to the plus charge, and I'm going to call that E plus, right? And then the charge due to the electric field due to the negative charge, E negative. So that's a negative charge. So when you have a negative charge in your equation, then you have that flips the direction of the unit vector, and so it's pointing towards the charge. And then this would be my total electric field right there. Okay, so I'm just the vector sum of those two. And you could do that anywhere, but we're not going to do that anywhere. We're going to do what's called the far field approximation on the axis. So if I have these two charges on the x-axis, I want to find the electric field somewhere on the x-axis far away. That's the far field approximation. So here's my observation location. I'm going to calculate the electric field due to this charge, and it's not at the origin, right? So this depends on this distance, which we're going to find, and that's E plus. And E minus is that way, but they're not the same, right? Even though the dipole has a net charge of 0, the electric field is not 0, because the electric field due to the negative charge is smaller in magnitude than the positive charge, so they're not going to cancel, and I'll end up with this right here, the electric field pointing to the right. So the first thing I need to do is to find the vector values for all these things, the location of the observation location, the positive charge, and the negative charge. So the positive charge, if they're separated by a distance s, then that's the origin. This is going to have an x value of s over 2. So it's s over 2, 0, 0. I'm using this angle bracket notation for vectors, x component, y component, z component, just because it's the best. The negative charge is at negative s over 2, 0, 0. And then the observation location, RO, I'm just going to call this distance from here to there, the scalar value r, and that's on the x-axis, r, 0, 0. Cool? Okay. So that's what we have right there. Now we're going to calculate, the first vector is the vector RO plus. I should have drawn this on there, but this is the vector from the positive charge to the observation location. We did this before, right? I just called it R, but I'm calling it RO plus because I have 2. I can't just call it R. I can have 2 R's. So the notation doesn't really matter. But it's the same thing. It's the observation location minus the position of the vector of the charge. And so I get this vector subtraction, which is not hard, right? Because I can say r minus s over 2 is r minus s over 2. 0 minus 0, 0 minus 0. So that's my RO plus. That's the vector from the charge to the observation location. And I'm going to put that in my electric field equation, 1 over 4 pi epsilon naught, Q, the magnitude of this, and then the unit vector. So the magnitude is really easy. We don't even have to do it, right? Because if I have a vector that's only in the x direction, then I'm going to take this squared plus this squared plus this squared square rooted. I just get r minus 2, minus s over 2. So the magnitude's pretty easy. We don't really need to worry about that. The unit vector RO plus is also pretty easy. It's just in the x direction. So I can just write 1, 0, 0, right? That's okay. That should be okay, right? That's not too hard. Now let's put these two things into my E plus vector, 1 over 4 pi epsilon naught Q, and then there's my magnitude, R minus S over 2. I have to square that, and there's my unit vector. That's not too bad. Okay, now let's go and do the negative charge. So the negative charge is at a location RO minus. So it's the observation location, R0, 0, minus the charge, negative charge, which is negative s over 2. So when I do r minus negative s over 2, I get r plus s over 2. But then I get 0, 0. So that's the only difference here. Then we can write our electric field. Now we have a negative charge. So I put negative q there, and that will, but my magnitude is different too. It's r plus s over 2. So there's two differences. The unit vector r 0 minus is still in the positive x direction, right? And don't try to make that, oh, it's negative because it's in the negative x direction. No, we already took into account that over here. Okay, so don't try to take that into account over here too. I have made that mistake and then before. So if you make the mistake, it's not a bad thing. It's just you got to make mistakes. So if I put that in, I get this. So I have the negative q. I have r plus s over 2 quantity squared, and then that same unit vector. Okay, now we can add those two together. So the electric field is this vector sum of those two. So here's my positive electric field. Here's my negative, the electric field due to the positive charge, and the electric field due to the negative charge. And if I want to add those two together, I can do that, right? Because this vector, 1, 0, 0, 1, 0, 0, I can factor that out. So I have this stuff, and then they both have that same vector, so it's pretty easy. They're in the same direction. And in fact, they also have this 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught. They also have a q. I can factor that out too. And I get this is just the x component, right? There's no y component. There's no z component. So I can just deal with the x component right here. So I have the q, 1 over 4 pi epsilon naught, 1 over this, and then negative. That's a negative right there. And that one's plus. Next, what I want to do is take that same expression, and I want to get a common denominator. So I can do that, right? If I multiply this fraction by r plus s over 2 quantity squared divided by r plus s over 2 squared, and then this one by the r minus s over 2 squared, top and bottom, and I get this. So when I multiply this top by r plus s over 2 squared, that's that. And then the bottom, I get the same common denominator. And then this one's going to be negative, right? That negative sign's right there. And then r minus s over 2 quantity squared. So what we're going to do now is to multiply the top of this out. So I can FOIL this, right? First inside, outside, last. First inside, outside, last. And I get this. So I get r squared. And then I get r times s over 2 plus s over 2 times r. So I get two of those. So it's just s r times s. And then I get s squared over 4. And then over here I get r squared, but there's a negative sign. And then I get negative of this, but there's a negative sign, so I get rs. And then I get s squared over 4, but then there's that negative sign. And you'll see here, those two cancel, r squared, negative r squared. S squared over 4 minus s squared over 4, those cancel. So I'm left with this. Q over 4 pi epsilon naught, 2rs. And then I have that stuff on the bottom. Okay, we haven't done the far field approximation. Now we're going to do the far field. So the far field approximation says, let's imagine that r is much greater than s. So it's not near the dipole. And we call this the far field approximation, which I cut off with my head, but whatever. So here's our expression that we have right now. And in the far field, I can say r is much greater than s, which means that this r minus s over 2 is approximately equal to this, which is r plus s over 2, right? If s is small, it doesn't matter if I add it or subtract it. I'm still about at r. And then those are about r, right? Because s is small. So that means that r minus s over 2 quantity squared is r squared, and r plus s over 2 quantity squared is r squared. And so this is r squared, that's r squared. So I get 2rs over r to the fourth. The r's cancel, and there is my electric field due to the far field approximation on the axis. So if we have something like this, we need to do some checks, right? Because we can't just leave it alone. Let's first check the units. So does this have the correct units for the electric field? Well, this is the electric field due to a point charge. We have 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, check. We have Q, and then we have Q over r squared right here. And this is distance divided by distance cubed. So it is 1 over r squared. So it does have the same units as the electric field due to a point charge. Good. Now, what should happen as r goes to infinity? As r goes to infinity, the electric field should go to 0, right? And that works right here. As r goes to 0 to infinity, as this gets bigger and bigger, that gets smaller. And then finally, what about if the two charges, as s goes to 0, the two charges are right on top of each other? If they're right on top of each other, there should be no electric field, right? They should perfectly cancel. So as s goes to 0, this goes to 0 too. So it's good. We're done. We're done with that. Now let's find an expression for the electric field on the perpendicular axis, so over here. So I can put my observation location up there. I have the electric field due to the positive charge, the electric field due to the negative charge, and then that's going to be the total. And you can see here those two fields are not in the same direction, so it's not as easy, but it actually is kind of easy. So here's my RO plus, right? So the vector RO plus is from the positive charge to the observation location. And so we need to find that, and then we'll need to find the minus one too. I didn't draw that one because I don't want to make it messy. So we still have the same vector location of R plus. It's still at S over 2, 0, 0. And we still have the vector location of R minus. I kept them in the same place. And then we have, this is now our vector location of the observation. So it's a distance R on the y-axis. So it's 0, R, 0. And now I can find RO plus. It's just going to be this minus this. So I get 0, R, 0 minus S over 2, 0, 0. And I get that. So it's not on the x-axis, but you can do that. You could do this by inspection too, but it's in the negative x direction and the positive y direction. So it's negative S over 2, R, 0. Now we can use this to find the electric field due to the positive charge. So this is just our electric field due to a point charge, constant, Q. I need to find the magnitude of that, and I need to find the unit vector, but I'm not gonna, right? So here's my RO plus vector. I don't want to find the magnitude and then find the unit vector because I'm be doing a little bit of work I don't need to do. So I'm going to use a trick. It's not a trick. It's not a trick. So remember that I can define the unit vector as RO plus divided by the magnitude of RO plus. Well, if I put that in over here, then I get, instead of that, I'm going to put in this. So I just put RO plus hat. I just put this in. And now I have, on the bottom, I have RO plus magnitude squared times RO plus magnitude. And that's just RO plus magnitude to the cubed. But then I have the vector on the top. So this is the same thing. Is that okay? Okay. Now I can find the magnitude. That I do need to do that. I did it the long way. S squared over 4 plus R squared plus 0 squared has a Z component. And then if I want to find that to the third power, I can write this as to the 1/2 power and then to the third power. So this is going to be S squared over 4 plus R squared to the 3/2 power. That's how I'm going to write that. And then the 0 left off. So let's plug this in. Let's plug that in. And I get this. So 1 over 4 pi epsilon naught Q. There's my magnitude cubed. And then there's my R hat vector. And I'm going to leave it right there. So we can leave that there for now. Now let's do the same thing for the negative charge. So here's my negative charge. I got the negative sign there. I need to find RO minus, which is this, right? So there's my RO minus. I skip a step? No, that is it. Yeah, I didn't show you where I got that from, but I think that's okay. And the unit vector, same trick. Same trick. This is important. Look at this. This is the same magnitude, right? For both the positive charges. They're the same distance away. So that makes things a little bit easier. And then I get this. So this is the same electric field except for one change. First, this is plus S over 2. The positive charge has minus S over 2, and then I have the minus there. But the magnitude to the third power is the same. Now we can just add those two up. So here's my positive electric field, the electric field due to the positive charge. And here's my negative. Now, you'll notice that if this term and this term are almost the same, if I factor out a negative out of here, I can make them the same. So if I factor out a negative, I get negative Q, but then this becomes positive, and then that has to become negative. So now I've done that, and look here, this term and that term are the same. So I can factor these out, and then just add these two vectors. So if I factor those two out of this addition, there's my common term, and then here are my two vectors, S over 2 R0 and S over 2 minus R0. So I just need to add those two vectors together. And you can see something magic happens here. The R and the negative R plus negative R is 0. S over 2 plus S over 2 is S. So this is my common term, still right down there. And then I have S, 0, 0. And then now we can use the far field approximation. So if R is much greater than S, that's the far field approximation, then this S squared over 4 plus R squared is approximately equal to R squared. And then if I take this term, R squared to the 3/2, it's just going to be R cubed. And so I get this as my far field approximation for the electric field. Notice it looks a lot like, 1, there's a negative sign. 2, we have a QS over R cubed, just like before, but we don't have the 2. That's the only difference. We don't have the 2. And then we can check units. Of course, the unit still works. I have charge over distance cubed squared, right? Because the distance over distance cubed. As R goes to infinity, yes, it goes to 0. And then as S goes to 0, yes, it goes to 0. So we're all set. Now, let's do one thing. I'm going to do live coding because you like live coding. If you don't care about Python, if you don't care about looking at far field approximation, stop here, okay? But if you do, let's do something else. I want to make a plot of, and let's just do on the axis. I want to plot the far field approximation versus the real value of the electric field, and we can see how they change. So here I'm going to do this in Python. Let's go ahead and make a graph. G1 equals graph. Title equals far field dipole. You gotta spell right. Is my camera shaking? Okay. And then I'm gonna say Y title. Let's just call that E in volt. Let's do newtons per coulomb. And then the X title is R in meters. And then I like to do this width equals, let's do 400 by 200, height equals 2. If you don't do this, it still works, but I have my screen zoomed in and it just doesn't look really nice. Now I'm really gonna make two graphs, right? So I'm gonna make two graphs. Let's call this FD for the dipole, G curve, color equals color dot red. And let's put this label equals dipole, real. And then FF is far field. It's going to be equal to G curve, color equals color dot blue, label, I can't spell, I'm worried about shaking that thing, equals far field. Now I need to determine my stuff. Let's do 1/4 pi epsilon naught I'm going to call K, and that's 9 times 10 to the 9th. And then Q, let's do 1 nanocoulomb, so 1 times 10 to the negative 9th. And then S is, I don't know, it doesn't really matter. Let's do a millimeter, so 1 times 10 to the negative 3. So I have all my values right there. The other thing I need to do is to start with my value of R, and then I'm going to keep moving R, right? So let's say R is equal to 2 times S, right? So I want to start outside the dipole. If I don't do that, I'm gonna pass over the dipole, and things are going to get whacked out of line. Let's first make a plot of, and then dr. I need to have how big of my step I'm going to do. Let's say S over 100. So now I can move my vector, my observation location using R, and find the electric field and plot it. So let's just plot the far field approximation, and then we'll come back and add the real. While R is less than, let's say, 5 times S. Right, so I'm going to go 5 distances away, and we can change that up later. Do the following. Number 1, calculate the dipole. So I'm going to write this as just ED, K times 2 times Q times S divided by R cubed. Right, that's my dipole equation right there. And now I'm going to plot that. FF dot plot R ED. And then I'm going to move my value of R. If I don't do that, I'll never end. So R equals R plus dr. And let's see if this works. It's a pretty simple program right there. It's not complicated. It worked. Yay. I always get scared. You know, you're doing things live. You never know what's going to happen. So this, it decreases as you get further away, and that's exactly what you expect. Now let's go ahead and calculate the actual electric field. So let's do this like this. R plus is going to be equal to, I'm just going to use scalars. I could do this as vectors. I should do it as vectors. Let's do this as vectors. It'll be more fun. So let's do this. R plus is the vector S over 2, 0, 0. And R minus is the vector negative S over 2, 0, 0. Now I'm down here. I'm going to say, okay, I'm going to calculate my observation location. RO is the vector R, 0, 0. So now it matches just what we're doing before. And now I can calculate RO plus. RO plus is going to be RO minus R plus. RO minus is RO minus R minus, right? Just like I did before. Now I can calculate E plus. E plus is going to be equal to K times Q times norm RO plus divided by mag RO plus squared, right? That's my actual electric field. It's a vector. I've calculated the vector value of the electric field right there. That's the unit vector R hat. That's the magnitude squared. R minus is going to be equal to K times negative K times Q, because the Q is negative now, times norm RO minus divided by mag RO minus squared. Then E real is just going to be EP plus EM. Now I want to plot that. So FR dot plot R, which is the scalar value, mag ER, right? Because I calculate the vector value, so I got to take the magnitude of that and plot it. And let's see what happens. This may not work. I didn't even save this. Let's save this. Dipole far field. And I'm going to give you a link to the code. Okay, so it's saved. Where's the code? There it goes. Okay. Why is it slow? Something happened. Can't find... Okay. I can fix that. If I don't make a mistake, I feel like something happens. Something happened. Oh, FR. Can't find variable FR. FF and FD. I just forgot what I did. So you can see here that as you get further and further away, the far field and the real values agree very much. But as you get closer and closer, they separate, which is exactly what we said, because that uses that approximation that R is much greater than S. And so when that's true, the two things agree. So there you go. The end. Okay. You could do the same thing for the off-axis, if on the perpendicular axis if you want, or even off-axis, because you can move R at any location. It's not going to work, right? Because we did the far field approximation assuming either on the axis or perpendicular axis. Okay, save that. Link to the code down below. Hope you found that useful. I will talk to you later.